Okay, so I'm starting.
Yeah.
Okay, so now I will go a little bit back and remind you what a topological space and what a manifold is. And then okay, so here's how it will go. So we'll go through topological spaces real quick, and then manifolds, just a brief review, and then we'll talk about coordinate, fiber, and vector bundles. Okay, so this is what we'll do. So, first of all, topological space. Now, assume you have a set. This is X. X is a set. You somehow wanna understand the structure of X, but to do that, just looking at a set is not enough. So you would understand what happens to X when you take X and map it somewhere else, like how the structure changes with this map, respective to this map. So what you do is you say, okay, let me choose some open sets, and I try to track what happens to them. So what you do is you choose some sets. So T, this is a collection of subsets of X, and you choose these. It really depends to you. This will be called the topology over X. I'll write that in a second. But the thing is, for this to work out most nicely and give you some useful information, you put some constraints on this. So what you do is you say, okay, the way you choose has to fit these three criteria. So first of all, you have to choose the empty set and X. I will use a little bit of abuse of notation and use this symbol. Although it's really not actually right to write this because this is not a set, rather a collection for set theoretic reasons, which I will not dive into. And then the second criteria is if you have open sets and you take the union over them, let me write alpha, you take the union over alpha, then this has to be in your open sets too. Now here, alpha can be any index. So it can be finitely many, it can be infinitely many, and these are U alpha are in T. So you can take finitely many of them, union them, they'll be open. Now the third criteria is if you have, again, open sets in your T, which we will call topology, and you take a union over them, this should also be, the intersection over them, this should also be in your topology. But here there's a point. So now we can only take intersection of finitely many of these. Now we can ask, okay, why we're taking infinitely many of these, it works. We're taking finite of this, why doesn't it work? The reason is, this is getting, well, okay, this actually comes from the way people chose to do topology, which is through open sets. So what people had in mind was, in like real numbers, you had this open intervals and everything worked out nicely, and you always looked in this open intervals and stuff. But the problem is if you small these intervals, and you take an intersection of them, then it reduces your point. And the point is not open, it's not an open interval, it's just a point. So people didn't want this. And when they generalized it, they realized that this might cause some problems in the general case. So they put this constraint that this index set needs to be finite in the intersection. Now, another good question to ask could have been, why do we use open sets? Like, why do we care about them in the first place? It's just convention. People used to do real analysis before, so they were already working with open intervals, and then they chose to continue with open intervals. You could define the same thing with closed sets too. Okay, anyway, if there's three constraints.
So I'm going to
yes.
kind of make the following question comment. So what's the physical meaning of an open set? Roughly.
Okay, well, it means like a neighborhood of something. Well, if you choose a point and you choose an open set around that point, it kind of means like you're looking at a neighborhood around that point.
Yeah. So that's the right idea. So how I've come to understand open sets at this point is that I have a set X, right? And I want to specify, in some sense, which points are close to each other. Do you agree? And so I specify this tau, which is the collection of my open sets. I specify which sets of points, in some sense, the points in that set are close to each other. And so it makes sense that, okay, in some sense, nothing and the whole space should be somehow close to each other because they're all in the same space. And then, okay, if I have a bunch of things that are close to each other, I take the union. That's still somehow close to each other. It's not close to each other. It's like degrees of being close to each other. Yes. But then the point is, I want to, if I have an open set, the open set should contain, all the points that are in some sense close to each other. So if I, like the example with the real line, if I had a bunch of open intervals, and then I took an intersection of infinitely many of them, I get a single point. And that no longer captures which points are actually close to that single point, right? There's still a bunch of other things around it. Right? So that's why you don't want infinite intersection, because then that might accidentally remove the points that are actually close to something. So open sets and topology is something about studying, degrees of closeness. So to what extent are things close to each other?
Mm-hmm. Okay, so if this is the scenario, if you can choose like open sets like this in tau, then you call X and tau a topological space, and the set can enjoy being a topological space, which is nice for him, whatever. Okay, so two basic examples. What would work anyway? Like right on top of does British say on top of your head, like for the first thing that comes in your mind?
Yeah, something like that.
Okay, examples. So what will be a very trivial thing to do to choose a topology on any given set? Like what is the smallest thing I can choose? Let me ask it like this. What? Sorry? Yeah, so empty set and yeah. So if we choose empty set and X and we declare these to be the tau and only these to be open, then this will work, right? So if you take the union, it's fine. If you take intersection, that will also be fine. So this is called the trivial topology. And this would work always. And what's the second thing you can choose? That's very, again...
like, think of this, but the exact opposite of it.
This is the less you can choose.
Janet can no longer answer.
Like, what's the most you can choose? Let me say it like that.
So let's start a bit further back. What are we trying to choose? What's the question? Question is, suppose I give you a topological space X. Let's define some very silly topologies on it. What is a topology? It is a go.
Like it is like X is the set, and then
yes.
How is like a collection of subset of X?
Yes.
A collection of subset of X.
We have X.
These three properties. Yeah. Okay. So what is one really simple collection of subsets of X that you can take? So one is nothing and X itself. Okay. But then what's kind of the opposite of taking, the bare minimum? The opposite of taking the bare minimum is taking
all the collection of.
Yeah, exactly. So taking the power set of X.
So you can also look at every possible subset of X, and that will of course satisfy all of these conditions. because every subset of X is a subset of X.
It will work because there can't be any problem. You take the union that's already here. You take every intersection that's already here. So that will work perfectly. Now these are the two ends of the scale. This is called the trivial topology. This is called the discrete topology. Now the topologies that we usually use are always in between these two, because these are kind of like, it's kind of trivial to see what would happen.
So yeah, like think of the first one is you say kind of all the points can be lumped into one category and all of them are close to each other, and you can't really distinguish between any 2 points using the first topology, right? I can't take two different sets and see, oh, this point's in this one and not in this one. Right? I can't distinguish. Here, I can distinguish between any 2 points using the topology because there's always kind of two different sets that 2 different points are in, which are completely disjointed, separated.
Okay, so if this seems counterintuitive to you and you don't like this, you can, whenever I say topological space, you can just think of Rn with topology defined as like open balls that you learn from analysis.
You should write that down.
Okay.
That should be example 3.
Example
3, the most important and only example that we kind of will think about for the most part. Well, I guess.
So Rn and with the set of open balls chosen as its topology, in a topological space.
So
well,
write this out.
Yeah.
So write down. So open sets UI such that for any point in X there's an open ball.
Oh, okay. Yeah.
Like write out the full definition and then draw a picture.
Can I give a reference to 257 and then?
No.
Okay. Sets U. Okay, let me write it such that for every X in U, there exists that's completely in U. Yes, so this will be the definition of it. And then so if this is your Rn, the open sets will be something like this. Well, open balls is like writing like a base for the topology, but I'm not going to go into that anyway. Yeah, or it can be something like this too. Like, who cares? You can take unions of some stuff, and then it'll give you something of this shape. Or you can even make like weird shapes.
The idea is around I have a set is considered open in Rn. If around any point I can fit a little open ball inside of that. So I take any set, like an open set, I take any point in that set, and I can fit an open ball around that point in that set. So these sets are considered open in Rn.
Okay. Now the second question that we can ask is, okay, topological space plus continuous functions. I lied to you. Okay, so we know how to define continuous functions from Rn to Rm for some n and m. I think I'm writing this horribly wrong, but I don't care. Okay, anyways, so if you know how to define continuous functions for this kind of topological spaces, now what if I ask you to generalize this to any topological space? How will you define it? Okay, I'm gonna give this one right away. So let's assume x and tau x, y and tau y are topological spaces. Okay, then a function from x to y is called continuous. T, nu, or something like this. If for every, okay, I'm gonna use again a piece of notation here, but I don't care. For every open set in Y, which means V is in topology of Y, if we take the pre-image of Y with respect to F, this will be in topology of X. So this means every open set comes from an open set. This literally means this. You take an open set, you go back, there's an open set that gives you that. If this seems counterintuitive to you, you can think of your topological spaces like Rn, and this will become just for every epsilon.
Draw a picture.
Okay, yeah. I just want to write it and then draw a picture.
No, I think you should
Okay.
draw a picture and not say.
Oh, that's also way too
Or
much.
you can write it down.
Oh, so this is Rn, this is Rm. Now, if there's a f that's continuous, this means that for any point you choose here, there's a for any epsilon, this is your epsilon. You take a ball like this, right? You take the points that are at most epsilon distant to your point x here, and then you look where this x was coming from. So this is the per-image of x. Then you know that there is a ball with delta radius, that this ball is mapped here. This exactly means for any open ball you choose here, there is an open ball that goes to this. Nothing else. So this is actually generalizing stuff, which I like it more because I find this more confusing.
And roughly, what are we saying with this in terms of topological space? Right? Open sets, I said were like kind of sets which tell you that some points are close to each other, right? So in this case, we're essentially defining continuity that if points are close to each other in the target space, then they had to have been close before the mapping as well. Okay?
Yes.
Roughly speaking.
Okay, now I will erase this.
Okay, wait, hold on. I think it's good to stop, take a sip of your tea, and then look at their confused faces and ask the question.
Yes.
So, should I have the P if and only if?
No, that's actually a good point to show. If well, yeah, because it's definition. No, I thought something like that. I thought, so here's one thing you can do. You can ask, what if you put another constraint and say that every open set needs to go to an open set with F? That will change the story a little bit, and that means that your open sets are one-to-one correspondence with each other in your two topological spaces, which essentially means that topologically you can't distinguish them. Because you have a set, they have open sets, and they're exactly corresponding to each other. And that will be called a homeomorphism, which we won't discuss today. But if you also put a constraint that goes backwards, that will work out nicely, and that's very useful.
We will discuss today when we talk about that.
Right, yeah. Okay, so let me write that then.
Hold on, just wait.
I'm just going to
I
erase
have
this
more
part.
questions. So this is just the definition. This is equivalent to the delta epsilon definition, right? And so the important part here is that it's the pre-image of an open set is an open set, not the other way. That's what we just said. That it's an open set here came from an open set here, but it's not necessarily true that an open set here will be mapped to an open set here. That's not necessary. Why? Because, for example, in principle, what I could do is I could take my entire space and map it to a single point. Do you agree? And so that would be, you know, a single point isn't necessarily an open set in the target space, but that map makes sense that it's continuous because kind of all the points are getting mapped to one thing.
Yes.
So, you know, everything that was close got mapped to something that's close.
So it's not giving you enough information, but you know, you still know something about the function. Okay, so definition. If f from x to y and g to y to x are continuous, so we have two dictionaries. One is from, this is English, and then this is Turkish. This is F. F is translating from English to Turkish, and G is translating from Turkish to English. Now, if are continuous such that if you compose these, now I write it in this order. So this is starting from Turkish. So this is coming from Y, going to X, and then going to Y again. So I can just don't say this and write it like Y. Is actually the identity on Y. And if I do the other way around, if I compose F with G, which is from X to X, is actually the identity on X, then we will call X and Y homeomorphic. Now, I wrote this maybe a little bit bad because I use F and G. This initially means that you have an inverse of F that's 1 to 1 and continuous to. So this is, so instead of saying this, you can just use this line.
It might be easier to rephrase this as
Yeah.
if I have two spaces and there is an invertible function that's continuous. So and the inverse is also continuous, then that's homeomorphic.
Yeah.
So if I have I can essentially map this space into this one continuously and this space into this one continuously. Have a projection. So it kind of says that all the open sets here will be the same as the open sets here. And that would be
So the
that would be
yeah.
the topological space for the same.
So then F is called a homomorphism, and then the spaces are called homeomorphic, which I think makes sense. Okay. So if you don't have any questions, I want to erase this and write manifolds here, so that we can keep the manifolds definition here at all times. Okay. Now we actually discussed manifolds, but I'm gonna, I just want to write a brief definition using topologicals. Well, what I'm gonna say is manifolds itself is a topological space too. That's what I wanna say. The only point I wanna make actually. Okay, so we went through this. Okay, manifolds. But there's too many indices here, so I don't want to mess them up. Okay, so a manifold itself is actually a topological space. Well, everything that I say here will be a topological space. It's a topological space that is locally Euclidean, but I don't know how to write Euclidean in English, so I'll just write this.
Euclidean is EUCL.
Just EU.
EU and then CL. Yeah, just C.
Okay.
There we go.
Why do people do this themselves? Euclidean. By Euclidean, we mean it's just Rn with the known topology from analysis too. So this is what these are called Euclideans. Yes.
So locally it looks like Rn, and if it locally looks like Rn, then you can put some coordinates.
So this is a definition that physicists will write. Now we will write the mathematical definition. So a topological space M is called N. Well, you can call it an N manifold, and then we'll denote the dimension of it here. N manifold if there is, so now we will write some stuff. First thing is such a covering with domains OI in M such that the union of OI is M. Well, this is just the definition of a covering, literally. You know, covering is you just take open sets and you loop, and then you cover your space. Okay. And then the second thing is we can define maps phi I from UI to VI, where VI are actually subsets of Rn. Now, we will call these guys charts. So these are called charts. Now we have two things that we need to have, and these need to satisfy some constraints, such that if you take any UI and any UJ, that intersection is non-empty. Well, this means, let me draw it here. So this is your UI, and this is your UJ. We have an intersection here, right? Now, this if you know how to take this part and map it to a subset of Rn, and if you know how to take this part and map it to a subset of Rn, then you should have a dictionary that translates how you map this green part and this yellow part in Rn, right? So if you live here, these are the words that are common in English and Turkish. And if you even write them a little bit different, there should be a way of knowing how to go write the other one, knowing the first one. Okay, so if this is the case, if it's non-empty, then, okay, so we do it. How to do this? So we have charts. We know how to take UIs and make them go to subsets of Rn. So let's use them. So let's take the intersection of, well, let's take the, forget the word.
The composition.
Yes, the composition of the J chart, but inverse of it, with E chart. Now this will go from right. Now this is starting from where the J charge took this place, and then it's taking it back with this, and then it's, so this is what it's doing. So we had, let's write this. So we had a chart that took this here. Let's say that this area is mapped here. So this is phi j of this intersection, let me call it U. So we take it back in green dictionary, and then we switch our dictionary to yellow, and then we again look where it goes. This is what this means. And the constraint we put on this,
I think that's a bit confusing. You should probably have a separate thing of Rn with your dictionary. It shouldn't be going to the same Rn because the image of phi j could look different. So draw a second patch somewhere below.
Yeah, okay, fair enough. Okay, let me actually make this smaller. Now draw it nicely. This is our manifold M. This is Rn, and then this is another copy of Rn.
And draw the whole set in each, and then have the intersection red or something.
Okay. So this is
draw
mapped
the whole
here,
thing, and then it has
but actually the intersection is here.
Yes.
And then this is taken here. Let's say it's something like this. and the intersection is here, actually. So what this is saying is you look at, so let's call this is J, and then this is I. This is I. Now you take where the Jth one went, but you only look at the intersection, so you're only caring about this part, and we take it back with I. We take the pre-image, which will give us here, and then we switch to yellow, and we take this area, and we put it here. Now the claim is these two areas that coincide in the intersections, these are actually homeomorphic. So this function will then be a homeomorphism.
So if it should be continuous and invertible.
Yes,
So
and the inverse will also be continuous.
Roughly speaking, let's take the analogy from last week. The analogy from last week, suppose you had some city, right? You had two maps for the city, one kind of for the, say north part of the city, one side for the south part of the city. But then there was a little region where the maps describe kind of the same part of the city, right? Then those two maps, like if I use one map or if I use the other map, it should be the same, right? There shouldn't be any difference. So that region of the map should be homeomorphic to that other region of the map. Right? So in other words, it should be the same. So if I have two different maps covering the same area, that part should be the same in each of the maps. Okay.
Okay, so this is basically what a manifold will mean in a topological sense. Good. So now we can come to the fun part. So bundles.
Hold on. Give people time. Right?
Yes.
And here you're saying, or in the definition, say that the topological space
Yes. So yeah, there's an abyss of. I should have said this. You're right. So the thing is, mathematicians are, they don't want to put so much energy. So what they do is they just call a set a topological space and don't write what the topology is, but they assume you to somehow basically know what the topology will be from the context.
Not necessarily. So the idea is I have some space that has a topology, and then I can separately give it coordinate charts. So for example, if I have a sphere, right, that has some topology that you can take from R3. Okay? And then I can separately give it, say, two charts, U1 and U2, so the stereographic projection from the top, stereographic projection from the bottom. So UI have to be open sets in the sense of the topology from, so they have to be open sets in the topology, but then those need not be all the open sets. So I shouldn't necessarily have every open set have a chart associated to it. I should just be able to cover it with some open sets. Right? Like the sphere, if you think of a sphere, I only need two charts to cover it, right? The kind of for the top half and for the bottom half. We discussed this last time with the stereographic projection. Remember, if I could like take a plane and then wrap it on top of a sphere. Yes? No? And not you then. Do you remember like
this
stereographic projection? Yes. And okay, we needed only kind of two sets to define the stereographic projection, right? And that will make it into a manifold. However, you know that a sphere has a lot more open sets than just kind of everything without one point and everything without another point. Agree? So those are just kind of to define charts on them, but then there can be many more open sets inside. And you know that there have to be many more open sets inside because if I have a chart from like a blob in coordinates, right? It has to be a homeomorphism to that little region of the set. Agree? If it has to be a homeomorphism to that region of the manifold, then you know inside of the open set in Rn there's like smaller open sets inside of that. Like if you take smaller balls that would fit inside. And that means there have to be corresponding open sets here that are smaller and inside the UL. Okay. And so this is kind of the, yes. And so how is this a little bit different than what we talked about last week? It's not really. But
It's the
last
same
week,
thing.
it's logically it's a little bit different. Last week I said that we didn't discuss topological spaces. Why? Because in principle, if I had just some object, like any set, and I just gave it coordinates in some way, such that the transition maps were homomorphisms from Rn to Rn, then I can actually define using these charts. I can kind of give this new space, give the manifold a topology from Rn if I have. Versus here, you're saying, okay, suppose the manifold was already a topological space, we can give it some coordinates. I was saying last week is that if you had any set and you were able to give it coordinates that satisfy these properties, maybe remove the word open from the word covering, then you can give it a topology that makes it.
Actually, it's no open in the covering.
Okay, no open in the covering.
Yes.
Even better.
So the two definitions are actually equivalent because this
the
means
exact same definition.
yeah. So if you have a topological space that you can associate coordinates, that like you can just forget the topology. If you have any set that you can assign coordinates, then you can just make it a topological space, right? So becoming a topological space is not too hard. You can yourself can become a topological space if you want too much. Okay. Anyway, so I'll keep this here. Maybe we'll need it afterwards. Now we're going to talk about bundles. Okay, so the first thing I'm going to define is something called coordinate bundles, which are not in many sources because it's something old. So this is actually the idea that bundles started with. And then people realized that they can generalize this notion. So it's actually useless to just talk about coordinate bundles. But I think it's a nice way of approach to introducing bundles. Okay, so okay, there's lots of letters here. So coordinate bundle definition. A coordinate bundle is a collection E, F, B, P, G, V, I, and J. Now, what are these guys? Let's get to know them. Let's get to know our participants in the competition. Where E is a topological space that is called the total space. And we will call this guy the total space. This will make sense in a minute. B is also a topological space, which we'll call the base space. F is something called the fiber, which is also a topological space. P is a projection map that's from E to B is a projection map in the usual sense, you know, the projection maps is coming from a set to another set. We each have also topologies, but who cares? G is a topological group Now I will say what a topological group is, because otherwise it wouldn't make sense. That acts on F effectively. Now at this point, I realize that I need to ask, do you know what a group is? No? So groups are essentially just ways of, it's a way to talk about symmetries. So you can take something and then you can look at the symmetries.
Hold on.
Maybe I'm thinking not going to what group does.
Okay, yeah. Sorry. Is this coordinate bundle your? I see. You're about to define like essentially an associated bundle, or what?
I'm just going to find the coordinate bundle.
Okay. Okay.
Coordinate
Maybe
bundle.
if people are really not familiar with the group,
Yes.
I think if we could actually just, I know you want to talk about this, but maybe skip, just discuss a fiber bundle instead,
Uh-huh.
and then we can at some point later discuss this if we feel like.
Instead of
Because
that, I
otherwise
was
it's a few too many things.
yeah. So I was instead of that, I was thinking not explaining the group part and everything else about coordinate bundle because it really doesn't affect
It will be too much.
too much.
It is too many new things at once. There's
Okay.
already many new things for people, and yes.
Okay.
So I guess there you EFB pi is perfect. Remove G, and remove I don't know what was J supposed to be.
This J is just an index set.
Okay, perfect. And then instead of coordinate, replace the word with fiber, and let's just stick to fiber bundles because that might be just more straightforward.
There's just a point I want to make in between coordinate bundles and fiber bundles, which is like fiber bundle is just a coordinate bundle with not giving coordinates. So that's why I want to keep these guys. But
Okay.
it wouldn't be a problem if I don't explain what G does. So I can just leave G here and say, okay, I'm not gonna do this. This we don't care about. This doesn't affect the definition anyways, by the way. So don't care.
Not needed.
It's just additional information which we don't necessarily need. Okay, so don't care what a G is. So VIs, so these VJs form a family of open covering of B. Okay, and then G is just the index set of G's. So G is the indexing. In a second, I will start drawing pictures and it will look nicer. Indexing set of J's such that for each J in J, this is the last thing I'm going to write. There is a homomorphism. Oh no, homomorphic, yes. Homomorphism phi j from this guy Vj, which was a open set on B, Cartesian product with the fiber to the pre-image of Vj. And these are called the coordinate functions. Okay, let's draw. So
Maybe draw on the second board and just draw a really big diagram on the second board. And then
okay, I can do that.
yeah.
Yes, I think this is good. So this is our base set B, base space. This guy's a topological space is happy. Now here, okay, let me write it like this. I wanna write it like this. This is E, which is the total space. Now we have VIs. VIs are essentially, maybe not like this, but maybe here. Yes, that will be nicer. So these are just covering V. These guys are VI, VJ, stuff like that. So they cover the I didn't write P here. The base space. Now we have a projection P. P does this. So P takes E and projects this to B. So one way of seeing this is like directly projecting, you know. I see like shining a light. So it takes this whole section of E and maybe projects it here. Like looking down on it. Like you can see it like if you had like a cylinder and then you shine the light on it, you know, that like that part will go to this part, like project to this part. So it's the same thing essentially, not necessarily a cylinder, but something more generalized. So we know what this is, this is, this is, this is. And let's talk about this part, the coordinate functions. So what these do is that it takes something here, suppose this guy over here. Let's call this one Vj. Now there's a fiber here that it takes. So this, I'm gonna write it here. So this is Vj. I just copied it here. And if we had a fiber, we just take the Cartesian product. So let's take this as the fiber. If you project it here, maybe your fiber is something like this. This is your fiber, F. And you took the Cartesian product with Vj. So for every point, so this means the Cartesian product, remember, just means that you, for every point of Vj, you create tuples like this. So this has tuples, V and F, for every V in Vj, and for every F in the fiber. You just create tuples like this. I should read this thing, not the cause confusion. Just, yes. So F is the fiber. So F is, small f is just an element of F here. Yes. Yes, exactly. So you can take every topological space. You can forget the topology. I'll just give you a set, right? So you can just take topological spaces and just Cartesian multiply them, and they'll give you the Cartesian product of sets. And you can define a topology depending on that, but we don't care it for now. No, any questions up to this point?
I want to draw the same picture, but slightly different.
Okay.
So, and kind of, I'll say words that you're probably going to say later. But kind of, what is the idea? I have, and I'll allude to kind of what we've talked about before and with Bloch's theorem and all of these things. So we have our base space B, which is hopefully some kind of manifold, so I can put coordinates onto it, right? Then I have this thing called a fiber F. Right, the fiber F is something. In our case, later we'll see. In our case, we'll care about when F is a vector space. Okay. And the point is that at every point of B, I have a fiber. So what I want to do is, somehow every point has some special space associated. So what I want to do is I want to glue to every point of B, I want to glue a fiber to it, right? So I want to have this, total space E, which is going to contain, roughly, it will, at least locally, look like B with a fiber attached to each point. So what do I need? I need a projection map, right? So I'm going to have kind of a fiber. So one yellow thing I'm using to draw, say it's a single fiber. So each one of these is F. And each fiber sits above some point in B. So say this is some point X, do you agree? Then the pre-image under the projection has to be homeomorphic, has to look like the fiber. Okay, so what I'm trying to do is I'm trying to take my topological space B and glue a fiber at every single point, right? And so, right, so then the total space E is kind of the manifold with a fiber glued at every point, right? So B is kind of the space to which I'm gluing things. F is the thing that I'm gluing. F is the thing that I'm gluing to every point. Okay, and then I have, okay, the projection is what kind of collapses the whole thing, forgets about the fiber, and just gives me back where the thing was glued to. Okay, and then the thing is, though, that this is not necessarily going to be as simple as just B cross F. Like, this is what you naively want to do. You want to look at the space B cross F, where at every point you just attach fiber, and so it's very nice and simple, and you're done. The problem is you can actually have, this is topologically too simple, and in some cases that's not necessarily not necessarily interesting. You can have something more complicated. So instead of demanding that the whole thing can be kind of split into a base piece and a fiber piece, what we really require is that locally, if I took a region here, do you agree? Above it, I will have something that, so if I have a UI, the thing that's kind of above it will look locally like just a simple product, but kind of globally, the whole thing may not need to be a single product. So locally, if I look at the pre-image of UI, so I look at kind of the stuff that's glued to some open set UI, then it will look like UI cross F. So locally, it looks literally like I have these points of B, and I glue these fibers at every single point. But then globally, that might not be the case, and then I think you'll have an example. But
Yep.
okay, I'll also just quickly draw one very simple example of a fiber bundle that people are already familiar with. So suppose my manifold was a circle, S1. So this was my B. People agree that a circle is a manifold, I can give it coordinates. Right? Okay. Then what I can then do is at every point I can attach a line to it. Agree? So at every point I can attach a line here, I can attach a line here. Okay. And these lines kind of keep going off to infinity. Do you agree? So what does this usually look like? This is a cylinder, correct? And so you can look at something S1 cross R. Okay? And so this is a trivial bundle, right? So this has no complicated twists, where the base space is S1, right? That's the base space. To each point I attach a line, right? And then I have a projection map which kind of takes a point here and just gives you back what the first coordinate is. Do you agree? And then I can also have these, trivializations where I can look at like an open set here and then see that locally it just looks like this little interval cross R. So did you kind of get now the idea of what we're trying to do? We're trying to glue some fiber at every point. And why will we need this is because from Bloch's theorem, we're going to like somehow use Bloch's theorem, and hopefully we'll have a nice enough space where my manifold will be my momentum space, and at every point I will glue a Hilbert space, and then I will study something interesting on that. But okay, yes, okay.
Yeah. Now I will repeat this, but in a slower and slightly different way. Yeah.
Yes.
So let's go back to the coordinate bundle. We haven't had a fiber bundle, right? So let's go to coordinate bundle. So what do we know? We only know that we have to define coordinates on our base space. Now we have B, and we have this VI's that we are calling the coordinates on B. Okay, so what does this say? This thing, this is the most important thing here. This part, this is saying something that he once said, but let's repeat it so it's easier to see. So we took this part out and we multiplied it with f. So this is just sticking f to every point. So here's like this one, just sticking f to every point, right? So there's tuples like this. Now the claim is this guy is homomorphic to this guy. This thing, that everything that gets projected to be J in the total space. Now, this does not mean that the total space is, so the total space is not base times f. It's just locally, it seems like this. Locally, because we know it seems like that on every chart that we chose. So this might or might not be the case. It's not necessarily the case. That's the interesting part of it. Now, here we only know that this is good for the covers that we choose, and then we can write something like this. So can I raise this part? Okay, good. Now I just want to erase this part, just note little things, and then boom, and what a fiber bundle is. This was our F. Okay, so now we can say a few things about this, right? The first thing that we can say is if we take this guy takes this times F, well, this times F, this part inside E. So this thing takes this guy and puts it inside E, and then projection just takes this part and projects it here. So this will just, if you put V and F inside it, it will just give you V. So V is not moved. We just stick a fiber up onto it, you put it in the base space, in a total space, and then you project it so you don't care about, you don't see the fiber anymore, and the point is always fixed. So nothing happens to the point for every V and F. Okay, now the second thing we can say about this. Well, actually, this is trivial, so I don't think I'm gonna write. Okay, this is about groups, so let me say this. If you have ij in your index set, so you chose two charts here on the base space, and okay, this is also about groups. So let me not discuss this. Sorry for the confusion. Okay, anyway, so this is the point of coordinate bundles. Now, observation. If you take the union of coordinate functions, let's say two coordinate functions is a coordinate function on the bundle. What I'm trying to say is, so you say you chose this VJs, but let's assume you chose some other VJs, and you have all this set up good. So you have two coordinate bundles whose base space, total space, fiber, and projections are the same. The only thing that differs is how you choose the coordinates. And you can take a union of these coordinates, and then you can look at that union of coordinates, right? So now everything still works. You can still attach fibers to each point in your covers, part of covers chart, and still map it in total space, still project it. Everything still works fine. So actually, the coordinates are not that important. Actually, you can get rid of the coordinates. that's the thing we're trying to make. Okay. Should I say this? No, I'm not gonna say this. And maybe I should say this verbally. So okay, let me write it here. So two coordinate bundles definition. Two coordinate bundles are called, oh, they're not saying this way, called strictly equivalent if this is strictly equivalent if they have the same, total space, base space, fiber projection, and G. Well, we don't care about G, but so this just ensures that your total space and your fiber works nicely in both scenarios. So it works same. It's the same kind of fiber that you're working with. Okay, and then we can say let's don't care about coordinates, and then let's look at the equivalence classes of coordinate bundles. I'm raising this, but I will draw stuff soon. So, definition, fiber bundles. Technically speaking, a fiber bundle in equivalence class, covalence class of coordinate bundles is a fiber bundle. Just realized I forgot to say something. This construction that I just drew here essentially means that you know how to put coordinates on B, and if you take B Cartesian product F, this means that you know how to put coordinates on this too, because this is just points of F. So for any point here, you know how to put coordinates. You know this, and then the second thing will be just a point of F, and this means by the coordinate functions, you can put this whole thing inside the total space, so you know how to put coordinates on the total space too. But anyways, okay, so fiber bundles is just the equivalence classes of coordinate bundles. And if you want to write this nicer, here it is. A fiber bundle is a collection. Now, what do we need now? We need the total space, the fiber, the base space, and the projection. Now, we can even forget about the group because no, this will be enough information, but okay, we haven't really discussed it. So, E is the total space, B is the base space, F is the fiber, P is from the total space to base space, projection map. Now here, this guy, for this guy, that's not this. So if you define fx to be the pre-image of the point x inside E, this is called the fiber over x. Okay, now we know how to define fiber bundles. Let's draw some pictures. So I was gonna ask this, but you spoiled it, so I know I cannot.
You can still ask it.
Okay, so suppose we chose S1 for a base space. So let's put a bunch of S1s. So these are S1s. Okay. And we want to form fiber bundles over this base space. Now, how can we do that? First, we have to choose our fiber. Well, what can we choose our fiber? Anything we want. Let's say I want to choose my fiber bundle to be I, which is the unit interval. Now, how can I stick this to S1? There's multiple ways, right? So I can just go ahead and stick it, and just stick it to every point. Now, I didn't draw it every point, but if you did, this will give you a cylinder. Now, the cylinder is your total space. So this is your E. And the projection just takes this line and projects it to this point. Now, what's the fiber? The fiber over any point is the pre-image, which is the line, which is this guy over here. Now, this is one way I can stick the lines. What's another way I can stick the lines? So this is not the only way we can stick. So what if I rotate the lines while I keep sticking them? Can I do that? What do you think will happen?
You mean like stick all the lines like in the middle of the, like all, covering all the S?
Yeah, we have to cover all the S. For every point in S, we have to stick the fiber somehow, because this says that. So this definition implies that if you take the pre-image at any point, this should be homomorphic to the fiber, which means that you stick fiber somehow to that point. No, we just have to stick it, but the way we stick is not constrained, so we can stick it any way that we want.
Right? Each of the lines that you attach at every point, they're kind of independent in some sense.
Yeah.
So I should be able to do that.
So let's say this. Can I take this for a second? So suppose we have something like this, okay? And then, can you come? I'm not sure. Do like this. So he is S1, okay? Just stick it up and down. He will be perfect S1. This is my fiber. I stick it at every point. I stick it. It will give a cylinder, right? Now, what if I take this, and while I stick it, I slightly rotate it? Like I slightly rotate it when I stick it, something like this. It will go like that. It will turn around. Now so, and while I rotate it, the thing I want to do is, since a fiber bundle is also a coordinate bundle, so if I take any covering of it, it should work out mostly. This means that if I stick this like this here, at the next point I can't stick it like this. If I look at locally, it should look like the Cartesian product. So if I stick it like this, the only thing I can stick it like this or like this, but I can't do like this. It should just differ a little bit, so that it's still homomorphic to the Cartesian product, right? So what will happen if I slightly rotate it around him? Now what will happen is, thank you, is you will get the Mobius strip. Okay, I should leave this back. So you will have something like this. Let's say that this was your S1. Let's open S1. but this point and this point are identified. So this is this. This point is the same as this one. And I stick the unit interval at each point. So I stick it, stick it, stick it. This will give me this paper, right? But this needs to stick with this one. So I can do this. Or I can turn it a little bit. And then stick it. Now if you were to do this, you will get the Mobius string. What's another way to do this? Let me make it thinner, I think it'll be helpful. I can rotate it 180, I can rotate it even more. I can rotate it even more if I want. And then I can stick it. Now if you look at this locally, if I take this neighborhood and you cut this paper through here, this is staying like this. Maybe something like this. You see there's some wrinkles on it, but at the end of the day, this is homeomorphic to this, the square. I can just push the paper and locally it will just be the square. But in your total space, it looks messed up, right? So it's nothing like the cylinder, it's something completely else. But we still locally get the square. So this is the whole point of fiber bundles. Locally, it looks like the Cartesian product, but the total space can look something else completely. Okay, so I can't draw a Mobius string nice enough.
And so the
Something like that. I just imagine it. I have this. Now another example I want to give, and then I'll talk about vector bundles, and then that'll be the last thing. Your computer was dead.
oh, my computer's dead.
Yeah,
That's
I
quite bad.
clicked.
I need to probably run out of charge. Hopefully the video isn't completely lost. Okay, you're gonna have to do some and not trip.
Okay. Yes. Yeah, and then the shape will be something like what? Sorry? Yeah. It will be the Cartesian product, and the thing will be what? Like, tell me a food like that. Not quite, because this isn't so cylinder. If you look at every point of S, it gives you line. This should give you something like this. Do you have a guess? This is one torus. Oh, you mean torus with one hole? Okay, yeah. So this is, you stick at every point you stick something like this, and this will give you, if you draw this nicely, a torus. So and this is your S. So your S1 is here. If you look at every point, you look at the fiber, it's S1. So you have something like this, and then you go around like that. So it gives you a donut, basically. So donut is a fiber bundle. Is it lost?
No, I think it's fine.
Okay. So what we obtained was, if you missed, a donut is a fiber bundle.
Yes. So yeah, if you imagine a donut, you can think of like it has like a lowest point at the bottom, right? Those points will create a circle, S1. And then from that, you can draw another circle at every point. And so you take a circle, if you do a circle at every point in a kind of simple way, you'll get a donut. And so in that case, your base manifold is the circle at the bottom, and then the fibers are the circles you attach at every point.
Okay, now let's look at a specific case of a fiber bundle. Now let's choose our fiber for physicists to be useful, right? So what do physicists care about? So for every particle in your system or every point at your system, what we want to do is we want to associate a vector space, right? Now, if you do that, this just means that we choose our fiber to be a vector space. So nothing too fancy. Let me check this. I'm not missing anything. Oh, it's here. Yes, okay. So vector bundle. A vector bundle is a fiber bundle with fiber a vector space. Now people like using the term rank of writing of a vector bundle. The rank just means rank of vector bundle is the dimension of vector space that's chosen as the fiber. So let me write it like that.
Okay, so what is a vector bundle going to be, roughly speaking? Question for the audience. It's going to be the same as a fiber bundle, but the only difference is that what's going to be what?
I mean, it has a direction.
Well, something will have a direction, but okay. In a fiber bundle, you had a fiber, right? And what did I do to this fiber? I had some base manifold, and I did what?
And then you attach each fiber to like the
Every point.
yeah.
Okay. Now here, the fiber is going to be what?
Be a vector space.
Exactly. It's going to be a vector space, and now we're going to attach a vector space at every point. Now, in fact, we've already seen two examples. Well, almost two examples of vector bundles, right? If I took an infinite cylinder.
Oh,
right?
I was gonna say that. Yeah. Okay.
There's many other things. For example, you've already seen this, right? If we took an infinite cylinder, that's already an example of a vector bundle where the vector space is what vector space? What's the vector space if I have that cylinder that I attach to every point of the circle?
So the base space is this thing in white.
Circle. That's where I'm attaching.
Yes.
I'm saying I'm going to attach a vector space at every point. In this case, I'm saying that I'm attaching a vector space at every point. What's the vector space I'm attaching?
It's the fiber.
Yeah.
What's
the vector space?
So for every point, we can see the fiber, right? So we take this point, and then we look at what's going on in the total space, and it's just this.
Yeah. What is that? What kind of vector space is that?
It's a
Yeah.
Yes.
So it's
what kind of vector space?
What's the rank of this vector bundle?
Or the dimension?
one dimension.
Yes,
Yeah.
I attach a one-dimensional vector space at every point.
This is the whole thing. So you can take this one-dimensional vector space and you stick it at every point, and they'll give you this that's infinite cylinder that goes up and down without getting tired, and that will be your vector bundle. Now you can ask, okay, what can't I do something like this? Can't I turn this vector space around while I stick it? Yes, you can. That's the whole point. Now, while you do this, it's hard to draw it like here, but assume instead of this intervals that you had one-dimensional vector spaces. So these lines don't end what they go and go and go. So, but
you can still rotate the whole line in the same way.
yeah. So you again have this guy, But while you stick it, you slightly start rotating, and then it kind of rotates and rotates. But it should rotate a little bit fast so it comes out nicely. But it will look like messed up. But if you take the Mobius strip and make at every line make it go at both directions, that will also give you a vector bundle with bundled one-dimensional vector space, but is not the trivial case. So this is the trivial case. The trivial bundle is exactly the, so let me, trivial cases. When the total space is just the base space Cartesian product of fiber, this is the trivial case. You can always do this. You can take any topological space B, and you can take any fiber, and you can take the Cartesian product, and that will give you a fiber bundle. If you take F to be a vector space, that will give you a vector bundle. You can always do this. But the most interesting ones are when the total space is not directly the Cartesian product. Because if we only cared about this, why would go ahead and define something this messy to study these kinds of things? We already know the Cartesian product, right? So this is the trivial case. Now, one other example that physicists say a lot, I don't know if we discussed it in this lecture yet. Tangent spaces. Did we discuss what tangent spaces are? I'm not sure. Did Sasha tell about tangent spaces? Okay, I remembered so. So remember 2 weeks ago, Sasha was talking about manifolds and tangent spaces, right? So you can see it like this. So what?
Sorry, what was a tangent space? First question. What was a tangent space? Do people remember?
Sorry?
Say that again?
Yes. So
Tangent to what? Yes.
yeah. Well, so the way to define this is like this. So for every point, you choose a point. So this is a hill. This is a nice hill. There's trees on it, maybe. So for every point on this, okay, maybe I have to like that. So for every point, you look at the tangent vectors on it, right? Maybe something like that, like this. So if you write it nicely, you can say this is actually a plane on your hill. So suppose you have this, and this is straight. This is your manifold, your base space, and for every point, suppose you chose this point, you stick a tangent plane to this point. So these is all the vectors that can be tangent at this point, right? So if this was your base space, and you looked at all the planes, and this is not, maybe this is a rectangle, but assume this is a plane, like it goes at all directions, and you stick it for every point of your base space, that will give you a vector bundle, with this being the base space, this being the fiber, and this stick to every point will be your total space, right? So if you do this for every point, you stick a plane, maybe something like this, and you do this for everything, and you call this hill M, or let's call it hill. The tangent space of the hill is a vector bundle. Now in this case, what's the rank of the vector bundle? Yes, so at every point, the vector space we stick to it is two-dimensional. So the rank of the vector bundle is 2. Okay.
So if you have an
Yes.
n-dimensional manifold, right? Its tangent space will have what rank? Yes, because if I roughly can put n-dimensional coordinates on it, right? Locally, I will have n directions to go in at every point. So the vector space I will attach at n point will be an n-dimensional one. And overall, the whole vector bundle will be a manifold of, so overall the tangent space is 2 n-dimensional, right? Because there's an n dimensions for the vector space in the fiber and n dimensions for the manifold itself, roughly.
Okay, so yes, this was briefly what I planned to talk about. So any questions?
here the fiber is a line, so
No,
fiber can be like
Yeah.
can be like circle like this, like go around like attach like a circle like to form donut.
so I didn't understand the question, but I'm assuming you're trying to ask that the fiber was a line. How did it become?
Yeah.
No, the fiber you choose, it can be anything. If you wish very much, you can choose a fiber to be a cat, right? You can just stick, if you can figure out how to stick a cat to every point continuously, then that cat can be your fiber. So the line, I, I gave it as an example because it's easy to see, easy to work with. But you can pretty much take it as one. You can take it some other kind of stuff. You can even take it like planes. You can just stick planes at every point to the circle.
And so it's just that other things are much more difficult to draw. These are the three examples that are the simplest to draw. So these
Yes.
are the examples that everybody talks about. Now, so one thing is that like in these drawings, one thing that we kind of don't explicitly say is how exactly we do this gluing, right? Because in principle, I need the projection map, the fiber, the total space, but then I also need some of these transition maps,
Yes.
right? I need to like tell you how this works in coordinates, and so when we draw this picture, we kind of don't explicitly say what the how to put coordinates on this, but in principle, you know, this picture somehow would tell you how to intuitively put coordinates on it, and you can formalize this. And I will hopefully write up some simple suggested exercises where you get some practice of explicitly looking at the definition and writing coordinates for some of these things, because it's a little tricky. Yes.
Yeah, so I didn't like write how the coordinate transformations. If we look at like a neighborhood in the base space, if we take an open, didn't write that because we already discussed them in the coordinate bundles. But the same thing applies here. Like if you take an open set in your base space and you take the pre-image, then it should be homeomorphic to that open set you choose, Cartesian product your fiber. So this is like we discussed it all in the coordinate bundles, and I said that this is an impulse because of coordinate bundles. So I didn't discuss it again.
So the idea is that kind of locally, my fiber bundle looks like the fiber cross an open set of the manifold. Right? So locally, I can think of it as like the fiber cross an open set of the manifold, and I can patch it off in this way and give it coordinates like this. So yeah, like roughly the idea is at every point, I stake something at every point, and locally it looks very simple, like you know, B cross F locally. But then globally, I could have these like twists. Right? So locally, if I look at this and I look at a specific cut, it looks like, oh, this is just a part of some cylinder. Right? But if I kind of look at the whole thing, oh wait a second, I realized that I did like a 180 twist. Right? So overall, it doesn't look like a cylinder, but locally, it just looks like S cross, you know, a little rectangle. So that's roughly the point of what we're trying to study. I'll write down some suggested exercises where you look at some simple examples and write this in coordinates, and that will be good. And then Janet, next week, well, sorry, not this Thursday, will hopefully tell us about finally about tight binding models, and then we'll kind of see more explicitly how Bloch's theorem appears in these calculations. And we will see that we'll kind of start talking about band theory in physics. And like the idea is kind of this idea that I've said before, that I will have some momentum space, which will be the base manifold. And then I will attach a Hilbert space at every point to this manifold. And we will get some bundle. It will be a trivial bundle. But then I will look at a specific part of it, and I'll get some non-trivial line bundle. And then we will study that. So the idea is I'll have some parameters, and at every point, I will attach a Hilbert space of states, and then we will just study this kind of fiber bundle where I have some parameter space, and for every set of parameters, I have a associated Hilbert space of states, and so then we will study how this kind of thing geometrically looks like and works. But yes, I'll write up some suggested exercises, hopefully by the end of the day. And I strongly urge that you at least like try and think about it, because this is this is non-trivial to fully understand from like, the first time you see, because it's a lot of definitions, and you should think about it at least once again. Okay.
Can I just say
Yeah.
this? So for every week there was like a reading. I mainly used this guy. I looked at various resources, but I don't know if this has a PDF. I stole this.
Lectures, I have no idea.
This is really nice. It like defines what a topological space continuous functions is, and it's like its way of writing is not like you can read it actually. It's not like you read the first paragraph and you're stuck. So you can I can send a picture of this.
Sure.
If I find a PDF of it.
The other thing is, I'm now realizing everyone in physics always says that Nakahara, wrote a good textbook called something like geometry,
Topology and something
topology
like
in physics or something like this, and that book is good and written for physicists. I've actually never opened that book. I should open that book because everyone says it's very good. So maybe I should have assigned readings from that. So I'll also link that.
Okay.
Right? Because really today we discussed a bunch of things, but the important thing that I want people to remember is just definition of a fiber bundle, and then the idea that a fiber can be a vector space. That's really good. Okay.
Okay.
I will stop the recording.